In this video, we're going to take a look at how calculus is done with polar coordinates. So we're going to start out quickly here. We're going to dive right into finding the derivative or the slope of the tangent line when we have a polar graph. So assume we have a polar graph. That is one where r is equal to some function of theta. Well, we know that your x value is going to be r cosine theta. Since r is a function of theta, we can call that f of theta times cosine of theta. Y is equal to r times sine of theta. So y now is equal to the function of theta times sine of theta. If this stuff throws you off, then go back and review the polar graphs stuff that we covered in the previous section. But we have a polar graph, which is written as r is equal to a function of theta. When I do the conversions, x is equal to r cosine theta, y is equal to r sine theta. So f function of theta times cosine theta is my x value. F of theta times sine of theta is my y value. Now, the derivative of y with respect to x, that is the standard derivative in rectangular form, which gives us the slope of the tangent line, is like change in y divided by change in x. And therefore, we can take a derivative of y with respect to theta and divide by derivative of x with respect to theta. Now, when you take a derivative of y is a product now of two functions, our f of theta times sine. So we take the normal f of theta times the derivative of sine, which is f theta times cosine, plus the derivative of f times normal sine, which is f prime times sine. So in other words, we're using the product rule to find the derivative of y with respect to theta in the numerator. In the denominator, we're going to do the exact same thing. We're going to use the product rule, but this time on the x. So normal f times the derivative of cosine is f times negative sine. F prime times normal cosine is f prime times cosine. Some people think of this as doing product rule of this x function in the denominator and product rule of the y function in the numerator. Other people will just memorize this formula or some equivalent version of it because obviously you can change the order up a little bit, change which things go on the right versus the left. But essentially it's that. So whether you want to think of this as just a product rule over a product rule, or whether you want to use the expression directly, either way is perfectly fine. So let's take a look at one of the polar equations we've seen before. Then we're going to use it to find slope of the tangent line at a couple of different values for theta, specifically when theta equals pi over 4 and when theta equals 0. The equation is going to be r equals 5. That is a circle of radius 5 centered at the pole. Let's go ahead and do the calculations. Now, as we have seen before, r is equal to a function of theta. In this case, r here is my constant, r equals 5. We could also find the derivative of that because this function here, f of theta, is my r. Again, there's two different ways to do this. You can think of it as derivative of y with respect to theta, with replacing this function with the actual value, in this case of 5. Or you could just use the formula. I'll do both ways in this case, but both ways are going to require me to have taken the derivative of r with respect to theta, which is 0. The derivative of any constant is 0. If I want to plug that into this formula, let's go ahead and take the formula. I would say my function is 5. The derivative of my function is 0. Function is 5. Derivative of my function is 0. Notice what that does. That 0 times sine and 0 in the numerator and 0 times cosine in the denominator go away. 5s will then cancel out. So I will just get negative cosine of theta divided by sine of theta. You could write that as cotangent as well, if you want to simplify that. I'll leave it as cosine over sine. So that's one way to do that, is to just plug in what we know of the formula. Here's the f, here's the f prime. That came from my r equals this function. Again, 5 was my function. And then r prime is 0, so the derivative of my function is 0. The other option that you have is to take y equals f sine theta and say, oh, that's just 5 times sine theta. Let me go ahead and do this another way. So the other option you could have done is say, my function is just 5. Since y is 5 sine theta, in the numerator, I take a derivative of that, y, with respect to theta, which would be 5 times cosine of theta. And in the denominator, derivative of 5 times cosine is negative 5 times sine, again, of theta. Same thing that we got above, negative cosine of theta divided by sine of theta. Either way you do this, you get the same thing. A lot of times, I use the formula just because that only basically forces me to do an f and figure out what f prime is, and then I plug it in. But some people like doing derivative of y divided by derivative of x with respect to theta, obviously. Now that we have the derivative, now we can say, what is the value when theta equals pi over 4, or when theta equals 0? So now that I have the derivative, and by derivative, I mean the standard derivative, dy dx, derivative of y with respect to x, I can say something like, what's going to happen when theta equals pi over 4? All I do is plug it in. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. So when that happens, I get negative 1. I won't do the rewrite or anything like that. When theta equals pi over 4, we get negative 1. Now, when theta equals 0, then that thing becomes, well, cosine of 0 is 1. Sine of 0 is 0. So we get this, which is obviously undefined. So we get an undefined tangent when theta equals 0. And this means we're going to get a vertical tangent, essentially. Let's take a look at this idea here. Let's take a look at these two. The original function, the graph of the original function, which we know is a circle radius 5, and then what's happening when theta equals pi over 4, and what's happening when theta equals 0. So here is the point when theta, excuse me, here's the circle of radius 5 drawn in Desmos, r equals 5. There's the point, 3 point, about 5,4, and again, about 3.54. So that's the point right there. You can see that the line tangent to this point on the circle should have slope pretty close to negative 1. So if we figure out the slope, again, negative 1, if I actually found that line, it'd be something like that. Oh, I'm not on the circle. There we go. Again, that's the tangent line. And as I move that around, if my angle theta were 0, I'd be here at the point 5,0. And obviously, slope of that tangent line is infinite. It's straight, it's a vertical tangent line. So that should make sense why when theta equals pi over 4, we get a slope of negative 1 for our tangent. And when theta equals 0, we get a vertical tangent on the r equals 5. Obviously, not every equation in polar form is going to be quite as simple as r equals 5, but we can still deal with more complex equations. Let's do this. We have r equals 4 times cosine of 3 theta. This is that rose curve with 3 petals that we saw in a previous video. Now let's find the derivative of this rose curve. In this case, I'm just going to use the formula directly. In order to do that, I have to first realize that r is equal to this function of theta. And so what I'm going to call r prime, somebody else would call f prime of theta. The derivative of 4 times cosine of 3 theta. Well, the derivative of cosine is negative sine. Our argument is 3 theta. And then I have to multiply times the derivative of the inside function, which is 3. When I take 4 times 3, I would get negative 12 times sine of 3 theta. So that's my r and my r prime. And I just replace the f of theta. Everywhere I see an f of theta, I'll replace that with 4 cosine of 3 theta. And everywhere I see an f prime, I'll replace that with minus 12 times sine of 3 theta. I'll do that in both the numerator and the denominator. And then I get this as my derivative. Now, obviously, I can simplify this if I want. We could probably use some trig identities if we'd really like to. I am not going to do that right now. I think it's fairly obvious that we could factor a 4 from the numerator and factor a 4 from the denominator and then cancel some things. You can also use trig identities with cosine 3 theta, sine theta, sine 3 theta, cosine theta. You could do the product to sum identities is what I'm getting at. And then some of those may cancel out because we have a 3 theta and a theta. And again, you could do a lot of stuff, a lot of simplification if you like. But this is it. This is the derivative of the Rose curve. And if we wanted to, we could figure out the actual values and get those specific values for the derivative. Now, I've actually done this and I've set up a little test here. So 4 cosine of 3 theta is this graph. And what I've done is I have put a point on this curve so that as I change the value of A, we can see that point go around the curve and kind of just follow our curve there. So that's what we're doing here. The other thing I did is I calculated the slope using that derivative formula. And at whatever point I'm at, we can calculate the slope. Of course, a tangent line is just y minus y1 equals slope times x minus x1, where we're at x1, we're at the point x1 comma y1. So if I look at the tangent line, sure enough, I am getting what looks to be the correct tangent line. And as I move A around, that tangent line looks like it follows the curve pretty well. Again, we're just moving this tangent line or moving the point around, and then it is automatically computing the slope of the tangent line. Ooh, that's a little fast. Let's see if I can, I don't know. Nope, too fast. All right, so if it automatically goes, it goes a little fast. But if I'm taking it through here. It's not too bad. So as you can see how that, as the point moves around, that is tracking the slope of the tangent line. That's slope is just a formula that we just found. So there we go. So while this formula does look complicated to find slope of the tangent line, it's actually not too bad. It's just a simple plug in whatever theta we're looking for and then compute. And it gives me the standard derivative of y with respect to x. So standard slope of the tangent line. Let's do another example of a graph that we saw in the previous section. So here we have r equals 3 plus 3 times cosine of theta. That's a limison, and it's in particular a cardioid because the constant and the coefficient of cosine are both equal. So 3 and 3 gives me a cardioid. If you want to try this on your own, push pause on the video. Otherwise, I will show you how this is done in a couple of seconds. In this case, our r prime is simply going to be, well, derivative of 3 times cosine theta. The 3 will go away, become a 0, and then 3 cosine theta, when we take a derivative of that, I get negative 3 times sine of theta. And that's it. That's all we need. Now we can go plug that into our derivative formula. Again, r equals a function of theta. So every time I see a function of theta here, I replace that with the r. Let me do that on a separate line. So replace that with, in this case, 3 plus 3 times cosine of theta. Be very careful when you do this because we should have parentheses around the 3 plus 3 cosine theta. When I take a derivative, I had 3 times sine theta. So this is minus 3 times sine of theta as my derivative. In the denominator, negative f of theta turns into negative 3 plus 3 times cosine of theta. And then the derivative obviously is a minus 3 times the sine of theta. By the way, there is some simplification you could do if you wanted to. So for instance, we could distribute this cosine in the top. Let me go ahead and do that just to make this a little bit easier. So we'd get 3 times cosine of theta, and then we'd get a plus 3 times cosine squared of theta. Then we'd have a minus 3 times sine squared of theta. And in the denominator, when you multiply this, it'd be negative 3 times sine of theta. Then you'd get a minus 3 times cosine theta sine theta. And notice that you get another minus 3 sine theta cosine theta. That's the same thing as cosine theta times sine theta. So technically we get minus 6. So minus 3 and another minus 3, you get minus 6 cosine theta times sine theta. So that's simplified a little bit more than before. Now, I pulled up a trig identity sheet just to show you what I'm going to do in the next step, but I'm going to use the trig identities sheet. Cosine of 2x or 2 theta is equal to cosine squared minus sine squared. And so I have something akin to that. I have a cosine squared minus sine squared in my problem. I also have a 2 sine cosine uh, in my problem as well. So I can simplify that using these double angle identities. I'm going to go backwards on them. So you don't have to do this by any means, but I'm going to just for the sake of simplification. So for the sake of simplification and making things look a little bit nicer, on the top I have 3 cosine of theta. That's not going to be simplified anything. But then I have 3 cosine squared minus 3 times sine squared. And we just saw cosine squared minus sine squared is cosine of 2 theta. So we get plus 3 multiplied times the cosine of 2 theta. And then in the denominator, we have minus 3 times sine of theta. And I said, if I have 2 times sine times cosine, that gives me sine of 2 theta. So if I factor the 6 into a 2 times 3, or a 3 times 2, that'd be better to write. 2 cosine theta sine theta becomes sine of 2 theta. So we get minus 3 multiplied times sine of 2 theta. Just using the trig identities. And moreover, if you want to factor out a 3 on the numerator and in the denominator, cancel them out, you could get that as well. So factor out a 3 in the numerator, factor out a 3 in the denominator, cancel things out, and you'd be left with something like this. There may be some trig identity that you can utilize here to make this simpler as well. I'm not going to at this stage. I think that's as simple as I need to make them. But there you go. And just like we've done before, if you wanted to plug in a certain value of theta and see what the slope of the corresponding tangent line would be, you could do that. If you wanted to find horizontal tangent lines, you'd figure out when the slope was 0. So when this was equal to 0. If you wanted to find vertical tangent lines, you'd figure out when the denominator was equal to 0 and the numerator was not equal to 0. And then check those, obviously. But that's the idea. There's the simplified version. And in our previous case, we could have also made a little bit simpler version using trig identities as well. I did the same thing with this graph as I did with the previous one. I graphed this polar equation, which in this case was a cardioid, not a rose curve like we had last time. And then I've labeled some point on there. And as that point moves around, I calculated the slope of the tangent line as cosine of theta, whatever theta I plugged in, plus cosine of 2 theta divided by negative sine of theta minus sine of 2 theta. And then as that point moves around, the tangent line will move around with it. And you can see that this is giving us what looks to be the slope of the tangent line. You can see a weird thing happens at that point at the origin. All right, by the way, that is the value of pi. Something really interesting happens at the value of pi. We get that. Okay. Oop, there we are. So you can see the tangent line move around, and you could figure out where we got horizontal tangent lines, where that's flat. Again, horizontal tangent lines happen when we have 0, so when the numerator is 0 and the denominator is not. And we have vertical tangent lines at a couple of different places. One is about right here. Again, that's when the denominator is 0 and the numerator is not. We also get a vertical tangent line about there. And obviously, in this, well, right here as well. So that tells you how to find derivative of this cardioid and what that would look like, what the slope of the tangent line would look like. I want to point out that this cardioid is not a function that we could have easily graphed in our rectangular form. The same thing with our previous example when we had a rose curve. We could not have graphed that very well in rectangular form. So finding a derivative in polar form is much, much nicer. Even if this derivative formula looks fairly complicated, it's much, much less complicated than trying to convert our rose curve or our cardioid back into a rectangular form. So that's the idea of derivatives in polar equations. Now, I know I just did the first derivative. Obviously, you could find, you could take this to second and third derivatives, although it's much messier after you do it. So I'm not going to do second and third derivatives in polar form. What I will do is we'll move into some area calculations. So derivatives give slopes of tangent lines. Antiderivatives have something to do with areas of functions. Now, in rectangular coordinates, we got area by using rectangles. We used really small rectangles, and they were the rectangles under the curve. And then we made these widths smaller and smaller and smaller, and we took the limit as the width goes to 0. We ended up getting integration, and that integration gave us the area under the curve. In polar functions, we're not going to be utilizing rectangles because the polar coordinate system doesn't use left, right, up, down coordinates. Rectangular, we use left, right, up, down, because that's X and Y. In polar, we're going to find the interior angle or interior area of a polar function. And because of the way polar is set up, we take little pi pieces and figure out the area of little pi pieces. So when I say a pi piece, I mean a little section of a circle. Remember that when we're talking about polar coordinates, r equals a number gives me a circle, and theta equals a number gives me a line through the origin. So these generating pieces will be lines through the origin and circles of certain radius. So I'm going to cut little pi sections out. Now, a little pi section is just a part of a circle. A circle has total area of pi times r squared, which if you think about it, is like going all the way around the circle. That gives you a rotation of 2 pi, dividing by 2, and then multiplying by radius squared. So any little pi piece is just going to be a section of a circle, a proportion of that circle, which is the change in angle from one angle to the next. Divide that by 2 because, again, the area of the entire circle is not 2 pi times r squared, but rather pi times r squared. So we divide it by 2 and then multiply times radius squared. So this is the diagram you end up with. But again, area of a pi piece is just change in angle theta divided by 2 times r squared. If you ever wonder about that, just think about what would happen with a quarter of the circle. So think about a quarter of a circle. That's 1/4 of a circle. That means the area of a quarter of a circle would be pi r squared divided by 4, which I'm going to write that way. So what I'm saying is that if we're talking about the change in angle for a quarter of a circle, it goes from angle 0 to angle pi over 2. So it would be pi over 2 down to 0, which is just pi over 2. So the area of a quarter of a circle is the same thing as our change in theta, that's pi over 2, divided by an extra 2, and then multiplied times r squared. Now think about if you had an eighth of a circle. So what would we have? We'd take pi over 8, and an eighth of the circle would go from angle 0 to angle pi over 4. So again, it'd be change in theta over 2 times radius squared. Now, obviously, this is all with a circle, but this happens with any type of graph that we want to draw. Imagine I drew something like this, which is not a circle, but let's say it's a petal of a rose curve, for instance. Well, I could take those same little sections and I could say that the R is actually the function value that gives me my rose curve. And I could let that R just be my function that generates out the rose curve. And the area is still going to be change in theta over 2 times r squared, at least an approximate area. And then when I take those change in thetas and I get smaller and smaller and smaller and smaller, then that's going to become an integration. That is going to generate out the area of an interior region of a polar graph. So that's how we do it. An area of an interior region of a polar graph, r equals a function of theta, is given by area. This is 1/2 times essentially r squared integrated with respect to theta from angle alpha to angle beta. And usually we set alpha and beta between 0 and 2 pi, where alpha is the smaller one. But that change in theta turns into an integration. R squared, again, is just my function r. And then I have a 1/2 out front because of the ratio of the area of a circle versus the change in my angle theta. It's always change in theta divided by 2 is the proportion of the area of circle. So that dividing by 2 shows up as a coefficient. So it's 1/2 r squared, integrate with respect to theta, and that's the area of an interior region of a polar graph. Let's look at one of the ones we previously saw. R equals 4 times cosine of 3 theta. We will find the area of one petal of this function. There's going to be 3 petals because it's a cosine of 3 theta. So we will figure out the area of one petal of that. For the most part, this is pretty straightforward. The big thing is that now we have the formula, 1/2 integrate from alpha to beta, my function squared with respect to theta. My function in this case is just 4 times cosine of 3 theta. So that's pretty straightforward. The only thing I really need to focus on is what the alpha and beta are going to be. Now, you can find these algebraically if you'd like. I might do that in just a moment. You can also find this on the TI-84. I can show that in another video. Or you can find it on Desmos. Let me just find these bounds on Desmos to show you kind of how I do it in general. But if you don't have access to Desmos, you can always use your TI-84, and I'll show you how to find the alpha and beta there as well. What I like to do is, whether it's on the TI-84 or Desmos, I like to graph the function, and then I either use the trace feature, and kind of get an approximate and use some common sense to figure out the approximate. But basically, we want to trace out one of these three loops. Now, because of the way this is graphed, not because of the way this graph, because of the nature of this function, all three loops are going to have the same area. It might not look like that right now. It might not look like that if you draw it on the TI-84, but they do in fact all have the same area. So it doesn't matter which loop we go from. I'm going to go from where we hit the pole or the origin, and I'm going to trace one loop out, doesn't matter which one, and then go to the next place where we hit the pole or origin. So as I start increasing my theta, and I would use trace if I was using the TI-84. If I start increasing my theta, I see that somewhere pretty close to a theta of 0.54, we cross over the origin. This is A here. And then we keep going. Maybe let's keep this label off. And when the theta comes back about somewhere close to 1.57, then we hit that origin again. So I just have to figure out, what do I think the angles are going to be? Well, 1.57 is about pi over 2. Point 0.54, or roughly there, 0.53, I guess. That's closer to pi over 6. Okay. So when in doubt, plug in that number. Plug in pi over 6 and see that in fact we do get right here at the origin. And then when I plug in pi over 2, see that I get exactly back to the origin. All right. So with pi over 6 and then pi over 2, we traced out this loop. Now you could have also started at pi over 2 and went around this other loop. Let me start that way. So start at pi over 2, about 1.56, 1.57, excuse me. Trace around this second loop. And when I get back here, we're at about 2.7-ish, 2.62 maybe, 2.62, 2.64, somewhere in there. And what could that be? Well, think about denominators. Denominator's probably going to be something that has to do with 6. That's actually 5 pi over 6. So from pi over 2 to 5 pi over 6 would give you a good one as well. And obviously I used positive angles. You could have also used negative angles as well. I could have traced out that first loop, the one that's sitting here on the right, if I would have went basically approximately, this is going to be negative pi over 6 all the way around to a positive pi over 6. So it's possible to use tracing the angle about and seeing that, for instance, if we integrate from negative pi over 6 to a positive pi over 6, that will trace out that right-hand loop. And then if I went from a positive pi over 6 to a essentially 3 pi over 6, that would trace out the second loop. And then if I went from 3 pi over 6 up to a 5 pi over 6, that would trace out the third loop. And in any of those integrations, you should end up with the same number. Let me go ahead and type that into my calculator. I have not typed that in yet, so it will be just a second, but we know how to integrate. If you don't know how to integrate in polar form, or if that throws you off, then I will put up a companion video to this, which shows you how to integrate using polar form. But in any case, we type that in, and I got approximately 4.19 for the area of one loop. Now I used 3 pi over 6 to 5 pi over 6. If somebody else goes from pi over 6 to 3 pi over 6, they should get the exact same value. And if somebody else went from negative pi over 6 to a positive pi over 6, they should also get the exact same value. And sure enough, when I typed it on my calculator, I got the exact same value in all three of those versions. So right about 4.19 is the area of one petal of this rose curve. You could probably do this by hand as well, although it might not be super fun. You'd have to use a trig identity substitution. Just a trig identity, excuse me. If you're having a hard time doing the tracing, again, I'll throw up a video that does companion video of how to trace in polar form and how to graph in polar form. But if you're having a hard time doing that, you can also do this by hand as well and figure out what theta values will work. In this case, I said it was easiest to see the start and end of a single rose petal if R is 0. In other words, if we were at the origin. So if you're trying to figure out values that work, all I have to do, and values that hit the origin, all you have to do is realize that when I hit the origin, R is 0. And so solving this equation, I would divide both sides by 4. And then say, when does cosine equal 0? Well, cosine equals 0 when the angle, which in this case is 3 theta, is equal to, well, it equals 0 when it's pi over 2, or I should say there's going to be infinitely many. Negative 3 pi over 2, negative pi over 2, positive pi over 2, and then positive 3 pi over 2, and then positive 5 pi over 2, and so on and so forth. Since 3 theta equals that, dividing everything by a 3 would give me that theta equals all of these things except for denominator being 2. I get denominator of 6. And so you can see that whenever you went from 1, 0 to the next, when theta went from negative pi over 6 to a positive pi over 6, that traced out one petal. And from pi over 6 to 3 pi over 6, that traced out another petal. And from 3 pi over 6 to 5 pi over 6, that traced out another petal. And you could still do that. 5 pi over 6 to 7 pi over 6, you get another petal. In fact, you'd get a repeat of one of the ones you've already found. And you could keep going through that. And then between any two bounds, that would work. Now, that works on this case because we cross over the origin a bunch of times. So we're trying to figure out when r is equal to 0. So that's the algebraic work if we want to find these bounds algebraically. And then obviously just pick 2 of them. I should say pick 2 subsequent, like the back-to-back versions. One for your alpha, one for your beta, whichever one we go with. So there is the area of one petal of the rose curve. Let's do another rose curve example. Here is r equals 6 times sine of 4 theta. Because we have an even number, 4, in front of our theta, we have 8 rather than 4 loops. So we have 8 loops here. And obviously 6 out front says that this rose curve is encircled by a circle of radius 6. If you want to try this on your own, go ahead. Otherwise, in a couple of seconds, I will show you how this one is done. First things first, the area of the interior of a polar graph is going to be 1/2 alpha, integrate alpha to beta, f squared with respect to theta. So the function I'm dealing with is straightforward, 6 times sine of 4 theta. So I'm going to square that whole thing and then integrate from alpha to beta. Now I can trace using my T84, using Desmos. I think, though, I'm going to solve this one by hand. We know this is a rose curve, and so we know it goes through the origin or through the pole. That is when r is equal to 0. So I am going to solve this equation where I set r equals 0, and then I'll solve for theta. Divide both sides by 6, we get 0 is equal to sine of 4 theta. And when is sine 0? Well, sine is 0 when the angle is equal to, well, there's infinitely many versions, but negative 2 pi, comma, negative pi, comma, 0, comma, pi, comma, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. You get the point. lots and lots of different places where my angle is going to be 0. So that's where sine is 0, when my angle is integer times pi. If I divide everything by 4, then, in fact, let me copy and paste this. It's going to be easier to divide everything by 4 this way. Divide both sides by 4. Zero divided by 4 is just 0. So we get that. If I want to trace out one curve, I just go back to back. So I'm going to go from 0 to pi over 4. So my alpha, I'm going to let be 0. My beta, I'm going to let be pi over 4. And there you go. If I do want to double check and confirm that I got this right, then I can look on Desmos, I can look on my calculator and see if I got that right. I'll go ahead and check this and just make sure through Desmos. Again, if you don't have access to Desmos, just use the trace feature on your calculator and graphing and polar coordinate systems. So here I have the angle 0, and as you can see, when I have theta equals 0, or in my case, I had to use the letter A equals 0 or theta equals 0, I'm at the origin. As we start having this point that moves around, that very first petal, the first time it comes back in contact with the origin, looks to be somewhere between 0.78 and 0.79, which is in fact where pi over 4 is. So if you instead just write pi over 4, sure enough, we're back at the origin. Sure enough, we're back at 0, 0. That's 0, 0 in the x, y, the rectangular coordinate system. And you'd get the same thing for any other trace out of whichever loop you wanted to trace out. And then like usual, I'm just going to plug this into my calculator. If you wanted to do this by hand, obviously you could, but that is not the goal of this video, to do it by hand. I'm just going to do it by calculator and get an approximate value of about 7.07. So that would be the area of one petal of r equals 6 times sine of 4 theta. That's how you would do it. It's pretty straightforward, except for maybe finding the bounds. And when you are finding the bounds, you can do so by algebraic approach like I did here, or by using the trace on your calculator to figure out where those things cross at. Let's look at another example. Here we have example 6. We want to find the area of the interior region of this graph, r equals 3 minus 2 times cosine of theta. Now this is a limacon with a dimple. So this is a dimpled limacon. And if you graph this, you'll notice that in this case, we never hit the pole or the origin. So if I'm trying to figure out algebraically my bounds, I can't set r equals 0. I'd have to set r is equal to another convenient number, which we'll see how that goes. in just a moment. Now, this one is probably easiest to do with utilizing your trace key. So I have 3 minus 2 times cosine theta here graphed out. Notice that when theta equals 0, I'm going to be at the rectangular point 1, 0. That would be an R of 1 if we're thinking about polar coordinates. And then I start moving around that limacon. And the next time I get back to that same value is when I hit 2 pi. Therefore, the interior of this limacon, this dimpled limacon, can be found by integrating from 0 all the way around to 2 pi. Again, I'm just utilizing the trace feature. 0 to 2 pi is what we're looking for. So what I would do is my standard thing. Alpha here we know is 0. Beta here we know is 2 pi. Again, that came from the trace. You could have also done this algebraically. In this case, you would want to set r equals 1 and then solve for that. You don't want to set r equals 0 because r is never 0 in this case. But if you set r equals 1, then what you can do is you can, in fact, solve this algebraically. Subtract 3 from both sides, you'd get -2 equals -2 times cosine of theta. Dividing by -2, you'd get cosine of theta is equal to 1. That is a positive 1. And then you'd say, well, what values of theta give me a cosine of theta that would be 1? And pretty obvious, theta would have to be something like an even times a pi. So you'd get something like -2 pi, and then 0, and then a +2 pi, and then a 4 pi, and et cetera, et cetera. So you just pick from 0 to 2 pi, and then you're all set. If you wanted to do this, again, by hand, there are other ways of doing that as well, but that's probably just the nicest one. Okay, again, it's unique when r is equal to 1. There are other values that for r, like if r were equal to 4, then it turns out there's a couple of different thetas that give you r equals 4. But a couple of different points on my limacon that give me r equals 4. But going back to the same point, r equals 1 is probably the best one to use. So we could find r that way algebraically too. That's the whole point. My function, that just gets replaced with 3 minus 2 times cosine of theta. Be very careful when you do that because that needs to be inside of parentheses. And the square needs to be applied to this entire function. If you only square the cosine, that's not going to be the same thing. So be careful when you do that. When I type that into my calculator, I got approximately 34.56, which if I wanted to give an exact value, it's actually 11 pi. This one has a really nice value, 11 pi. Which is kind of surprising given that we have this weird dimpled shape, that we got an area that was so nice. So that area there, shaded, is integer 11 times pi. But that's it. That's the area of the interior region of that limacon. It got a really nice value. So, by the way, I should have pointed that out in a couple of our previous cases as well. In this case, when we got that 7.07, that was actually just 2.25 times pi. And in the other case where we were dealing with Rose curves, so the Rose curve, um, the other case, example 4, that was essentially 1 1/3 or 4/3 times pi. Interestingly enough. Let's try example 7. If you want to try this on your own, go ahead and push pause on the video. I'll give you a couple of seconds and then I will show you how it's done. So the inner loop is the tinier loop of this limacon. So it is the smaller loop inside. If you want to find this bigger loop uh, without the smaller loop or the entire interior, then you'd have to do something different. But inner loop is traced out. Now, if you start at theta equals 0, it actually starts out here. So it's actually nice to start your count at theta equals something that gets you to the origin. It's hard to see in this case, but basically when we change, let's change this to pi over 2 and this to positive pi, I guess. Maybe it'll make it easier. So, oh, there we go. We get close to the origin at about negative 1.05, which hopefully you can recognize is about negative pi over 3. And then you start going around. When you hit 0, you're at this point. And when you come back to the origin, basically you're at positive pi over 3. So using the trace, we go from negative pi over 3 to a positive pi over 3. And that traces out my inner loop. Now, that's not the only way we could have done that. We could have also done this algebraically by realizing that inner loop starts and stops when r is equal to 0. And then I could have solved that equation for theta. And if I would have solved that equation, I would have said, when does cosine equal positive 1/2? And where cosine is equal to positive 1/2 on the unit circle means that theta is equal to, well, you guessed it, negative pi over 3 up to positive pi over 3. And then you'd add 2 pi to that. So I think the next time you get there is a 5 pi over 3. Or maybe, yeah, I believe 5 pi over 3. So the inner loop goes from negative pi over 3 to positive pi over 3. And then it would start back up at a 5 pi over 3 and then go to 7 pi over 3. So you could have also went from 5 pi over 3 to 7 pi over 3. By the way, going from pi over 3 to 5 pi over 3, that is not an inner loop. That's going basically around the outside of that loop. So you have to be careful. We want to go around the inner loop. So you go from negative pi over 3 to 5, excuse me, to positive pi over 3, or you start at 5 pi over 3 and go to 7 pi over 3. Either way, we're good to go. So I would use negative pi over 3 to positive pi over 3 as my bounds. And then obviously this is 2 minus 4 times cosine of theta. And this is just an input into our calculator. So as I input that into my calculator, I haven't done this into my calculator yet, but I will. When I did that, I ended up with about a 2.17-ish, about a 2.17. So there we go. That is the area of the inner loop of that limison with an inner loop. Let's try this one as well. If you want to try this on your own, by all means, go ahead and try it. In a couple of seconds, I will show you how it is done. All right, again, this is a limison with an inner loop, and we'll be able to see that inner loop if I graph it. So here I have graphed that polar graph, that limison with an inner loop. And you'll notice that if I'm tracing this out, the inner loop, we kind of start at roughly 0.4 or maybe 0.42 or somewhere in there. And then it traces out around that inner loop and it comes back and it hits the origin close to about 0.27-ish, maybe a little bit more, maybe 2.74, 2.72. And you might not recognize this decimal version, even if you got a really tight decimal. And the reason for that is that this decimal version is not a nice angle that we know. Let me explain that algebraically. So if we do this algebraically, Obviously, we're looking at when does R become 0? Well, R becomes 0 if I subtract 2 and then divide by -5 when sine of theta is 2/5. Well, that is not a really nice numerical value. We're going to get two versions for theta. If I force theta to be between 0 and 2 pi, I get two versions of that. One where I just take an inverse sine of 2/5. That's where I get the about 0.41 number. So let me call that one alpha because that'll be what we get there. It'll be the sine inverse of 2/5. All right. And again, that's approximately 0.41. And then the beta, well, how am I going to get that? We have to remember our properties of the unit circle. And how I would end up with this, I'd take 2 pi minus that number. Or I'm sorry, pi minus that number. Excuse me, not 2 pi. Pi minus that number. So if I take pi minus the inverse sine of 2/5, then I'll get that roughly 2.73 number. Again, remember how that works on the unit circle. Hopefully you remember how that works on the unit circle. If you do forget, just let me remind you that if we have the unit circle, that's a circle of radius 1 centered at the origin. And if I found the inverse sine of 2/5, that means we're at this angle here, where the sine value or the y value was 2/5. So that 0.4 there is 2/5. The other point that has the same y value or the same sine is going to be this point over here, about right here, which I can find by taking pi and then minus the angle that I just found. So the angle is about 0.4115 radians, and it gives me a sine value of 2/5 or 0.4. And the other angle is the one over here. The other angle with the same positive 2/5 as my sine is going to be this one. And this one over here. And that also has y value of 0.4 or sine value of 0.4, 2/5. So that's what I'm saying, pi minus that. In any case, that's my exact alpha and my exact beta. Some people would use their trace feature. And if all I would say is that if you are using your trace feature, don't just round to 2 decimal places, round to as many decimals as they'll give out. So if you wanted to use the exact value, or if you wanted to use the decimal version, um, both are okay. But if you are using the decimal version, go out as far as you can. Okay. So alpha starts at the inverse sign of 2/5, and beta ends at pi minus the inverse sign of 2/5. And again, if you're okay with an approximation, you can just use the decimal versions or the decimal versions on your trace feature. But remember, the r is 2 minus 5 times sine theta, so that's my function, 2 minus 5 times sine of theta. That's something that I can plug in. Obviously, it looks pretty messy when I plugged it in, but it's still very much doable on a calculator. I haven't done that yet, so let me do that. All right, now I've typed it in and I got an approximate value of about, 5.38. By the way, again, you'd get that same thing if you went out enough decimal places. If you went from 0.4115 up to like 2.730, you'd get the same thing. Again, rounded maybe slightly different, but to 2 decimal places, we're all right. Again, if you went out to about 4 decimal places on your alpha and about 4 decimal places in your beta, you'd be all right. So that's how we do these integrations. And that's how we find the area of this inner loop. Now, this one is not a nice pi times something. If you divide this by pi, you don't get a nice decimal version of something. The same thing was true for the inner loop of 2 minus 4 cosine theta. We got about 2.17, but that was not a nice pi times something. The first three we did, like I said, had really nice exact values that you could have come up with. So that very first one, when we had the rose curve with 3 petals, that area actually came out to 4/3 pi. I know I gave you the decimal version earlier. The rose curve with with 8 petals, that came out as 9/4 times pi, which again, I gave you the decimal version. And then the interior region of that limison, which was dimpled, came out to 11 pi. I did give you that exact version, but so those three had really nice exact values, whereas the inner loop problems that we just did, even when we had the nice bounds from negative pi over 3 to pi over 3, that did not have a nice exact version. And then on this last one we did, that did not have a really nice exact version either. It wasn't just a rational number times pi, a nice rational number times pi. All right, so that's how to find area of the interior of a polar function. That is what we do every time we try to find area with finding the interior region of some polar graph. Area is 1/2 integrate from alpha to beta. Usually alpha and beta are somewhere between 0 and 2 pi. We did see a couple of examples where we used a negative value for our alpha, and that was okay too. But integrate from alpha to beta, my function squared with respect to theta. The next concept with calculus topics that we're going to look at is the concept of arc length in polar form. Let's say f is a continuous function which has a continuous derivative on the interval theta going from alpha to beta. Let me change that up real quick. That looks a little bit better. So my angle is going from alpha to beta. Well, arc length is that square root of things squared. And what we're going to do is we're going to take the regular f of theta, square it, plus the derivative of f of theta, square it, add those things up, and then take the square root of the whole thing, and then integrate that from alpha to beta. Oftentimes, because r is equal to a function of theta, I think of that as the square root of r squared plus r prime squared. That is r squared plus the derivative of r with respect to theta squared, integrated from alpha to beta. Again, the formula looks very similar to our other arc length formulas that we've looked at before. We've looked at arc length in parametric. We've looked at arc length in rectangular. And arc length in polar is similar but different. And you could imagine what we're doing here. We're getting little bitty straight lines and then adding them up, and then it's turning into this formula here. Let's take an example that we know what should happen on, and let's see if it works the way we think it should. Let's find the arc length or the length of the curve over a given interval. My function is r equals 8 in polar form, and my interval goes from 0 to 2 pi. That is, theta goes from 0 to 2 pi. This, I don't even need to graph it right now. The big formula looks like this. Again, what I typically do is I typically think of this as r squared plus r prime squared. So that's how I typically think about that. And here r is equal to 8. So if r is equal to 8, then the derivative with respect to theta is equal to 0. So if r is equal to 8, the derivative is 0. So that's what I can plug in. I can take this and plug in an r of 8 and an r prime of 0. This one's pretty easy to do by hand because it says we're integrating from 0 to 2 pi. If you want to do it by hand, by all means, do it by hand. You can also plug it into your calculator. What you end up with is 16 pi. By the way, I said we actually should have known that when I initially started. And the reason I should have known that is that this is just a circle of radius 8. What is the arc length of a circle of radius 8? Well, it is the circumference of the circle of radius 8. And the circumference of a circle of radius 8 is 2 times radius times pi. Radius 8 would be 2 times 8 times pi, which is 16 pi. So we've confirmed that we get the right value, at least in this case of the circle of radius 8. You can see that any circle of any radius, if I said what is the arc length of the circle of radius, we'll call it A. Well, if A is a number, then the derivative of R is 0. You'd get square root of A squared, which is just an A, integrated from 0 to 2 pi. And that would give you 2 times A times pi. Again, you could, I'm doing this in my head, but you could do it by hand. I'm skipping a few steps, but that's what's happening. So there we go. We confirm that circumference of a circle is in fact 2 times radius times pi. Let's do another example. Now, this is a little bit uninteresting because it's also a circle, but R is equal to 4 sine theta, and we'll let theta go from 0 to pi. Again, this was the graph of a circle or laid out along the y-axis or along the line theta equals pi over 2. If you want to try this on your own, go ahead and do that. Otherwise, I'll do it in a couple of seconds. So we're finding the length of this curve. I need the r and the derivative of r with respect to theta. That's why sometimes people don't use just r prime. A lot of people use dr d theta because they want to make sure it's done with respect to theta. I will just use r prime as a short. R prime is equal to derivative of sine is cosine, so that's 4 times the cosine of theta. So that's what we get. 4 times the sine of theta, quantity squared, plus 4 times the cosine of theta, quantity squared, all underneath a square root. And we're going to be integrating from 0 up to pi. I'll do a little bit of simplification here. This is going to be 16 sine squared plus 16 cosine squared. We know that sine squared plus cosine squared is 1. So if I factor out a 16, I get 16 times 1. So I get the square root of 16 times 1 integrated with respect to theta. Square root of 16 is just 4. When I integrate that, guess I should put an equal sign right there. When I integrate that, if I do this by hand, I end up with 4 pi. And by the way, just as a check, when you graph this for sine theta, r equals 4 sine theta, you do get a circle of radius 2 lined up along the line theta equals pi over 2. In fact, I'll just graph that right now. So there we go. We get a circle of radius 2. And what we're saying is that if we start our point here at theta equals 0, and we go all the way around till we hit theta equals pi, we would have actually navigated that circle around 1 time. We would have navigated around that circle 1 time. All right. So from theta of 0 to theta of pi, I went once around that circle. And so I got the circumference of the circle. Weirdly, in this case, I didn't have to go from 0 to 2 pi because of just the way the polar equation works. So there we go. 0 to pi gives you 1 loop around this circle. Circumference should be 4 pi. And it is, as we saw. Let's do a more interesting one that we don't know yet. Let's find the length of one petal of the following rose curve. R equals 7 times sine of 5 theta. This is a rose curve with 5 petals on it, and we're going to find the length of one petal, or the arc length of one petal. Try this on your own if you'd like. Push pause on the video so you have time to do it. I will do it in a couple of seconds. In this case, we get this curve. If I want to trace out one petal, I might as well start at this first one here. We start at the pole when theta is equal to 0. And if I start going around, I go around my first petal and I get back to the pole at about 0.63-ish, pretty close to 0.63, which, if you think about it, is going to be pi over 5. All right. When do I get 0 for sine? Well, at integer times pi, then divide by 5. You get pi over 5. So from 0 to pi over 5, that's going to be my bounds for one petal. At least this one. And then you could have done pi over 5 to 2 pi over 5 for my next petal, and then et cetera, et cetera. So if we're doing this, first thing I want to do is well, doesn't matter, I guess, which one you do first, but we're going to find the derivative and we're going to find the bounds. We found the bounds first, technically, but also taking the derivative. If I take the derivative of sine, I get cosine. And then I'd have to multiply times the derivative of the inside function, which would be 5. 5 times 7 is 35. I'd get 35 times cosine of 5 theta. That's my derivative. So now I'm ready to plug everything in. Like I said just a second ago, if I want to do the first loop, it's from 0 to pi over 5. You could figure that out algebraically as well. by setting r equal to 0. The r squared is going to be 7 times sine of 5 theta, quantity squared. R prime is going to be 35 times cosine of 5 theta, quantity squared. So that's the arc length. Let me move out of the way there. And then that's something I'd probably just type into my calculator, which obviously you could try to do some simplifications. The simplifications on this are not nearly as easy to do as the simplifications on the previous couple of examples. When I let my calculator do the thing, I ended up with about 14.71 as the length of one petal of that rose curve. You may be able to go through the whole process and get something nice, get a nice specific value for this, but I'm not going to do that on this one. That would be not a fun integral to do by hand. So approximations are just fine with me. So this shows you how to find arc length. And obviously in the first couple of examples, we found arc length. We had really nice numbers. We ended up with 4 pi. We ended up with 2 times, well, this was originally 8, but 2 times a times pi, or 2 times whatever radius we're dealing with times pi. And then obviously this last one petal of the rose curve, was not a nice integer times pi or anything like that. It was roughly 14.71. But this is the formula for arc length in polar form. Again, I've been using r and r prime as my symbols instead of f of theta and f prime of theta. Now, if we have arc length, it's a short jump going from arc length to surface area. If we do surface area, basically, depending on whether I'm rotating around the polar axis or rotating around the line theta equals pi over 2, we're going to get different surface area formulas. There we go. So we're going to have this nice function. R equals a function of theta on an interval alpha between alpha and beta. And if we're going around the polar axis is another name for the x-axis. It's the line theta equals 0. So if we're rotating around the polar axis, then the radius is a y value. And the y value we know is r times sine of theta. So we just multiply our arc length formula by 2 pi times radius, which is in this case a y value, times my arc length square root, and then integrate that from alpha to beta. Now, in order for this to work, we do have to have r is a nice function of theta. It has to have a continuous derivative over the span from alpha to beta. In my Calc 2 classes, I won't give you a problem where r is a function of theta without a continuous derivative. But that's it. So surface area in polar, if we're rotating around the polar axis, which think x-axis, is 2 pi times my y value times my arc length square root integrated from alpha to beta. What's going to happen if we rotate around theta equals pi over 2? That would be the y-axis. Well, if I rotate around theta equals pi over 2, then instead of my radius being a y value, my radius is going to be the x value, which is r times cosine of theta. So we get that the surface area is 2 pi, integrate from alpha to beta, my function times cosine times square root of a really big quantity, which is function squared plus derivative of function squared, all integrated with respect to theta. Again, we have to have our r equals function of theta be a function with continuous derivative for this to work. Again, theta equals pi over 2, think that's the y-axis. Let's do a couple of problems here. Let's take r equals 6 times cosine of theta on the interval from 0 to pi over 2 and rotate that around the polar axis. Now the polar axis is, again, think of the same thing as the x-axis. 6 cosine theta, that's a full circle if I went from 0 to pi. But going from 0 to pi over 2 actually gives me just the top half of that circle. So I'm taking the top half of that circle and rotating it around the polar axis. Most of this is just plug it in and figure out what's happening. The only thing I really have to put any work into is figuring out the derivative. And in this case, derivative, or a lot of times I just say r prime, is equal to negative 6 times the sine of theta. Be careful when you plug things in. Alpha is clearly 0. Beta is clearly pi over 2. There's no worries about that. But oftentimes people will, instead of plugging in the actual function times sine of theta, they'll just plug in the function, or they'll just plug in the derivative instead of the actual function. So this is the function times sine of theta. The function is 6 cosine theta. And then we multiply times sine of theta. Then underneath the square root, I have my function, which is 6 times cosine of theta. And then I have the derivative of my function, both being squared and then added up. The derivative is negative 6 times sine of theta being squared and then added up. Now this one you can actually do a little bit of work by hand. It's actually pretty straightforward if you do it by hand. Nothing crazy here. This is 6 cosine squared plus quantity negative 6 sine squared. Cosine squared plus sine squared is going to be equal to 1. This negative 6, when I square it, is going to turn into a 36. This 6, when I square it, turns into a 36. So I'm going to end up with 36 times cosine squared plus 36 times sine squared, which when we add those up just gives me 36. Square root of 36 is 6. If I take 6 on the back end times 6 in the front end, I get 36 there as well. And then essentially you're integrating this. Again, I'm trying to do this as much as I can by hand, but if you want to type this original thing into your calculator, be my guest, go ahead and do that. That's perfectly fine. If you want to do this by hand though, you could use a U substitution. U would be equal to sine theta, and then du is cosine d theta. And you could, yeah, integrate with respect to u, get a u squared over 2, and you're off to the races. But if you want to type it in, you can type it in by hand as well. So doesn't matter. Whichever way you feel most comfortable, you can type it in that way or do it by hand. Again, it's not hard to do by hand if you wanted to do that. In this case, you get 36 times pi. (36 times pi is equal to the surface area formed by revolving the top half of that circle around the polar axis. By the way, what am I getting there? I'm getting a sphere of radius 3 when I do that. So 36 times pi is what I ended up getting. So 6 times cosine theta is this circle here, the whole circle. But if I'm going from 0 to pi over 2, I'm just tracing out the top half. And so I'm taking the top half of that circle, rotating it around the x-axis, and I'm getting a sphere of radius 3. And it turns out that the sphere of radius 3, well, the sphere of any radius has surface area of 4 pi times radius squared. That is, the surface area of the sphere is 4 pi times radius squared. I said this particular sphere would have radius 3. And so 4 times 3 squared is where we get that 36 from. 4 times 9 is 36. So you could have gone and done this whole thing by hand and proved that the surface area of a sphere is 4 pi times radius squared. There are easier ways to do it than this example, but this example is one example where you can see that. So there you go. There's the surface area of this object revolved around the polar axis. We got 36 pi, which meshed with our surface area of a sphere that we knew was going to happen. Let's do one more surface area problem. Find the area of this surface, the surface formed by revolving the curve around the given line. We're going to take our rose curve with 3 petals. We're going to take one of those petals, the petal that goes from pi over 2 to 5 pi over 6, and we're going to revolve it around the line theta equals pi over 2. Again, think that's the y-axis. So here's our curve 4 cosine 3 theta. We're going to rotate it around theta equals pi over 2 and on the interval from pi over 2 to 5 pi over 6. Now, just to be clear, I wanted to draw this. So this is 4 cosine of 3 theta. We get these 3 petals. The one that we're actually tracing out is the one that is currently in the second quadrant. So if you look at that petal in the second quadrant, that's the one we trace out from pi over 2 to 5 pi over 6. So from 3 pi over 6 to 5 pi over 6, or pi over 2 to 5 pi over 6, it's the loop or the petal in quadrant 2 there. And I'm going to rotate that around the line theta equals pi over 2. It's set up pretty well for me. Again, the only really thing I have to do calculus-wise is take a derivative before I start integrating. If I take a derivative of cosine of 3 theta, I'm going to get negative 3 times the sine of 3 theta. So I end up with negative 12 times the sine of 3 theta as the derivative. Because I'm rotating around the line theta equals pi over 2, my radius is just going to be my x value, which is r times cosine theta. R here, I guess I can say that's the surface area. My r here is equal to 4 cosine of 3 theta. So that replaces this f of theta. And then the other f of theta also gets replaced with a 4 times cosine of 3 theta. And then obviously the derivative gets replaced with negative 12 times the sine of 3 theta. Now there are ways to simplify and rewrite this. Oh, I forgot. I'm integrating from pi over 2 up to 5 pi over 6. There are ways to rewrite this and try to integrate this by hand. For the purposes of this video, that's not important. Obviously, if you were tested on how to do this by hand, you'd have to use some trig identities and some simplification processes, but it's okay. That's not, it's not crazy, but it's not very fun either. So I'm just going to take this whole thing and type it into my calculator and get an approximate answer. Now, when I type this in, I got about a negative 58.60. Now, here's why I got a negative. Remember that my petal was in the second quadrant. And because my petal was in the second quadrant, my radius would have been a negative number as I type in my function here. So really, I should have put an absolute value around this because every radius is going to technically be 0 minus this number. And therefore, I should have put technically a negative there. Hopefully, we're all smart enough to see that actually what we should have gotten for a surface area was a positive 58.60, which again, I don't know if that's a really nice or a messy looking exact value. When I divided by pi, it didn't give me anything interesting, but there you go. So again, the reason why this came out as a negative was because my radius technically came from my x value, and every time in this example, my x value was to the left of the y-axis, or in other words, to the left of the line theta equals pi over 2. So I got a negative x value, which was a negative radius, which led to a negative 58.60. Again, if I don't want that, just realize that technically I should have had positive radius. Technically, but not a big deal. So that's what I would have had if I took this loop and revolved it around the line theta equals pi over 2. Again, I'm getting negatives because we're all to the left. All these x values are negatives. Again, when I say that loop, I am specifically stating just that one loop, not the other two. So there we go. That's the surface area of revolving that loop around the line theta equals pi over 2. In this video, we found derivatives, we found interior area, we found arc length, and we found surface area using polar equations. Obviously, there's other calculus topics you could do with polar equations as well, but we won't touch on those for this class. So that concludes doing the calculus topics with our polar coordinate systems.